recording there? Okay, plus or minus our interval, 95% confidence interval for the amount of time that smokers thought had passed after 45 seconds. It's going to be equal to the mean of the time that they reported, plus or minus. Now, we're going to have to decide whether to use a z-score here or a t-score. Okay, so you guys tell me, which would you use here, z-score or a t-score in this particular place? Okay, I got one opinion of T, one opinion of Z. T. Most of you guys, I got 5 out of 6, 8 out of 9 are saying T score. Okay, well, the reason why we wouldn't use the Z score is that our Z, in this case, we don't know the population standard deviation. The only time we can justify using the Z score, which simplifies things for us considerably, the only time we can do that is when we know the standard deviation of the whole population. We don't know that. We only know the standard deviation of this sample, which estimates the population standard deviation, but it may not be exactly the same. And the other case where we can use it is when we're basing our standard deviation or standard error based on the standard deviation of a sample, but that sample size is very large. And by very large, we mean, say, bigger than 30 for our purposes. Okay, so we don't know the population standard deviation, and our sample size is less than 30, so we have to use a t-score. Okay, so it's going to be x bar plus or minus. Okay, it's going to be equal to plus or minus our t-score. T-score for alpha equals 0.05, 5% chance of being wrong. Okay, times our standard error. Okay, that's a little sloppy, but you guys get it. Okay, so now we have to go and look up our t-score. So I'm going to get a t-table here. Okay, let me see if I can't find a t-table. Let's see, maybe I'll type in Agresti, it'll help. Z-score, here we go. Here's a t-table from the textbook. And our number of degrees of freedom is going to be equal to our sample size minus 1. And the t-score that we want is for a 95% confidence interval. It's going to be this column in the middle. And 19 degrees of freedom is going to be equal to 2.09. I'm going to round it off for our purposes. So our confidence interval is going to be equal to, the mean, which is 59.3, plus our t-score, which is 2.09, times our standard error, which is 2.199. Okay, I'm going to put this into parentheses so I make sure it does it in the right order. I'm hoping that'll work now. Let me hit enter and see if it works. And the high end is going to be equal to 63.89. The low end is going to be equal to, x bar, our mean, minus 2.09, our t-score, times our standard error. Okay, let's put this in parentheses so it works right. And that's going to be equal to 54.70. Everybody get that? Everybody agree with that so far? Okay. When do we subtract the degrees of freedom? We do both. We add it and subtract it in order to get a range. We add it to get the high end of the range. We subtract it to get the low end of the range. Okay. So our prediction for the true mean amount of time that smokers will report for a 45-second period is between 54.7 and 63.9 seconds. Okay, so somewhere in between there, we think we're 95% sure the real mean is. Well, now, in this particular case, there's a real number that we're comparing this to. And that real number, it's not like we're comparing it to another group or an unknown or a population that we don't know the mean of. We know that the real answer, the correct answer, should have been 45 seconds. Right? So if our objective is to determine whether smokers significantly guess significantly different than the real time for a period of 45 seconds, we just need to compare our 95% confidence interval to the value 45, that single value 45. Okay, so we're 95% sure that the mean time that smokers think was 45 seconds is between 54 and 64 seconds. Well, that means that we're 95% confident that it's not 45 seconds, because if that would be outside of this range that we have 95% confidence that the real mean for these smokers would be. So we're comparing a sample with its own standard deviation, and we're estimating a population's distribution and standard error based on and sampling distribution based on that, and we're comparing it to a known value of 45 seconds. So by using the confidence interval, we can say that we are 95% certain that smokers guess wrong, guess different than 45 seconds when they try to estimate a 45-second interval. Okay, now we didn't do non-smokers here, did we? That would have been a second group to see if non-smokers. We kind of assumed that smokers would, half of them would get underestimated, overestimated, and so on and so forth. That, of course, may not be true. So we took a lot of liberties here. Okay, so now I'm going to take a look at this from another perspective. Another way of looking at this is for me to say, well, how many standard deviations apart is what I think the mean is and the value that I'm comparing it to? Okay, so I only have one standard deviation here, or one standard error. It's 2.199. That's my standard error for this sample. Okay, I'm comparing it to a value, so I only have one standard error that's involved in this whole thing, one standard deviation and one standard error. So if I want to compare how many standard deviations apart this number and this number are, I could just say to myself, okay, well, I'm going to say that for the moment, I'm going to call this Z. Z is equal to, now stay calm, everybody. I'm going to go back and review that. Z is equal to, what is Z equal to when we look at a normal distribution? It's equal to X bar minus what we think the mean is, the true mean is, mu, right, divided by the standard error. Okay, so now what's that going to be in this case? Z is going to be, or T. Now I'm going to change that to T. The reason why I'm going to change it to T is because in reality, right, we only have a sample size of 20 here, right? So we don't really have a right to expect this to follow a Z distribution as opposed to a T distribution. Okay. Now I'm gonna change this back to a Z for the moment and make believe it's a bigger sample size, just so we can go through this for the first time. Okay. So Z is equal to X bar, right? X bar is equal to 59.3 is equal to 59.3 minus the mean that we really think it is, 45, over the standard error, which is 2.199. Okay, so we want to know how many standard deviations apart these two values are. And it turns out there's 6.5 standard deviations apart. Now we know that if I were to pull up the Z table, okay, if I were to pull up the Z table, they don't even have 6 standard deviations apart. The highest they go is 3.49, right? 3.5 standard deviations apart in either direction. They don't go that far because the probability of getting that result is so small that it's insignificant past 3 standard deviations apart. It's super, super unlikely that you would see a result where you'd have the two groups would be the same and be that far apart when you took a sample like this. Okay, so a sample this size. Okay, so now we could say with almost 100% certainty, with 99.99, remember, because the chances of being wrong are less than 0.00001, the last percentage, the last area on that Z table. It's less than that, 0.0001, right? We can say with that level of certainty, or a p-value, with a p-value, right, less than 0.0001, right? With a p-value probability of less than that there is a difference between what these guys estimated and the 45 seconds. Well, now let's go back to this idea of using Z or T. We can't really use the Z table by all rights. We have to use the T table. Okay, now let's go and take a look at that T table. Remember that the number of T values, T scores apart, is still 6.5. We'd still calculate it the same way, but it would be a T score and follow the T distribution instead of the Z distribution. So let's look at our T table again. T table, Agresti. Okay, let's bring that back up here. Well, notice that number one, unlike the Z table, the T table depends on the sample size, the degrees of freedom. So I have to work with only this line here of 19 since the sample size is 20. So I'm only working with this particular line. Well, if I'm working with this particular line, I don't really get I can't really go to a certain number of standard deviations and figure out what area is represented by them. This only works for discrete values of the of t, right? In other words, if t is 2.09, that means that my p-value is 0.02, two-tailed p-value is 0.025, right tail and left tail, you add double that because you want to count for error on both sides, right? Because they only give you right tail here. So 5% chance of being wrong. So if the t-value is 2.0993, I have 5% chance of being wrong. If it's 2.539, I have 1% on each end, I have 2% chance of being wrong. If it's 2.861, I have 1% chance of being wrong. If it's 3.6, I have 0.02, excuse me, 0.2% chance of being wrong, right? Or 0.002 if we look at it as a proportion. So, and it stops there. Unlike the Z table, it doesn't give me an exact p-value. It gives me a range. If I had a t-score of, say, 2.3, right? 2.3 would have been between this number and this number for 19 degrees of freedom. That means that my p-value would be between 5% and 2%. So the t-table gives me a lot of information, but it only gives me a range for the p-value. Okay, just like 95% confidence interval, kind of like the way 95% confidence interval tells you if you can be 95% certain that two things are different, but it doesn't really tell you how exactly certain you are. This gives you a bit more information, but not as much as a z-table gets. Are we relatively, you don't have to really understand that too well, but are we relatively comfortable with that notion of how this T table and that Z table work a little bit differently? Okay, we do all see that they work differently, right? The T table and the Z table. They really do kind of the same thing, but because for every sample size you would need a table just like the Z tables for every sample size. So avoid having to print 97 pages in a textbook. They just give you a summary of the most common t-scores that you might be interested in. So let's move on from there. Okay, so now that's how we would compare this. So our t-score comes up to be this number. Well, there is a function. What did we do here? We took the number of standard deviations over the standard error. We calculated the standard error from the standard deviation of the square root of n, right? We actually measured a value for t, and then we used a table or Excel or some other device. Actually, you could actually do t distribution in Excel. You could cheat a little bit and see the value of t is 6.5. We know the degrees of freedom are 19, and we know it's a two-tailed test. It actually will give us the actual p-value. It turns out it's 0.000. So Excel actually, unlike the book, which only gives you a single table for every degree of freedom, Excel would actually, using that tdist function, actually give you a real number for the p-value. But we're not too concerned about that. Really, what we did here was we figured out the number of standard deviations apart. We represented that by calling it t represents the number of standard deviations.